Okay, so we kind of looked at distribution. We kind of see that binomial distributions kind of tend to look normal, sometimes at least. Let's look at another example. NASCAR cards and cereal boxes. Cereal company puts 1 of 5 cards into a cereal box. Each card features a different driver. We've got all these different drivers. 5 of them, it looks like. So I think it's 5. 1, 2, 3, 4, 5. Suppose the company printed 20,000 of each card, so there were 100,000 total. If a person bought 4 boxes at random, let X equal the number of cards featuring Danica Patrick. So it kind of looks like they're setting up a binomial model. We're going to select 4 boxes, so my N is 4, and I'm recording the number of successes. So is this a binomial setting? Let's do the bins. Binomial. Either I get a Danica Patrick card or I don't. Set number of trials, independence, and same probability for success. So the idea here is if I pick the first box, if it has a Danica Patrick card, it's going to change the probability that the next one has a Danica Patrick card, because instead of 20,000 out of 100,000, it's going to be like 19,999 out of 9. We've talked about this before, but it doesn't change it all that much. Technically, though, we don't have independence or the same probability. This is not binomial. Let's calculate the probability you get no Danica Patrick cards. So probability you get no Danica Patrick cards. Well, you got to not get a Danica Patrick card in the first one. That's 80,000. 20,000 are Danica Patrick, so 80,000 are not. Times, that's the probability the first one is not Danica Patrick card. Times the probability that the second one is not. Well, now there's 7,999 out of 99999 times. Now there's going to be one less non-Danica Patrick and one less total. Luckily, I only have to do this 4 times because I want to get 79997 over 99997. So I'm going to pause the video while I type this in the calculator. So I typed this into the calculator. I think that's right. If I hit enter, it's so amazing that the calculator can do that. Control enter. 40959. 40959. 40959. So about 41%. So there's a 41% chance you don't get any Danica Patrick cards in 4 picks. Use a binomial model to calculate this probability. Okay, so let's just pretend, after all, as you can see, yes, the probability changes after each trial but it doesn't change that much. We got a lot of cards and it's a pretty minute change. What if we were to assume that even though there isn't independence, let's just pretend that there was and use the binomial formula. So if we assume it's binomial, again, which it's not, and we select 4 cards, and the probability of success is 1 out of 5, 20 out of 100,000, 20,000 out of 100,000 is 1/5. And we want the probability that we get no Danica Patrick cards. So this, I like to use a formula. 4, choose 0. Probability of success raised to the, I got to get 0 successes. And then the probability of a failure raised to the 4th power. Just to let you know, 4, choose 0. How many ways can you choose 0 cards out of 4? There's only one way. This is 1. So it's really just 4/5 to the 4th power. And that should kind of make sense. This is 4/5. But instead of just this slight change each time, it's just 4/5 times 4/5 times 4/5. So let's take parenthesis 4/5 raised to the 4th power. So look at there. This one was that. This one is that. So these only differ by 0.000006. They're practically the same. This was 0.4096. Very, very close, about 41%. So this is a pretty good approximation. You might say, well, why would I do this approximation? This wasn't that hard, but this does get really hard. Imagine you got 250 trials and 100,000 people, and then there's all the different combinations. The binomial model has that one formula. It's still computation heavy, but at least the numbers are better than this, right? So sometimes we want to use a binomial model to approximate this non-binomial model. So when are these approximations going to be pretty good approximations of this? It's not always going to work. Kind of depends upon how many people are in the population. It depends upon how many we're choosing for our, I want to say sample, I shouldn't use the word sample, how many we're selecting out of it. And it also is going to kind of depend upon, actually no it's not, I'm not going to say that. I was going to say it depends upon this, but I don't think it does. So this is called the 10% condition. This lets us know whenever we can use this approximation. If we select n objects from a population big N without replacement, if our sample size is less than 10% of our population size, then we can assume the lack of independence will not have much of an effect on the binomial probability calculations. In other words, if the number we pick from the population is less than 10% of the population, then our binomial probabilities are good estimators, good estimates for the true probability. So we could use this if we want. In this case, I guess. I don't really have an example of it other than just talking about it. All right. Let's try to get this next page done in 3 minutes. Mean and standard deviation of the binomial random variable. If a count x of successes has the binomial distribution with the number of trials n and the probability of success p, then the mean and standard deviation are, so these are going to be formulas on the formula sheet. The mean is going to be n times p, and the standard deviation is going to be the square root of np. I like to write it as npq. That's, our book doesn't use it, but q is basically the complement of p. It's the probability of a failure. Now, in class, I like to prove that, I like to justify both of these. This one's actually pretty straightforward. I mean, if you take, 100 shots, playing basketball, you take 100 shots, and the probability that you make a shot is 20%, right? Then how many shots would you expect to make? That's not a stretch. You're going to take 20% of 100, say 20 shots, right? You just take p times n. So this is really pretty common sense. This one is kind of it's a direct consequence of the variance formula, the adding of variances for independent trials. I'm not going to prove it here, I'm sorry, but I might in class, we'll see. You don't really need to know the proof of it, but that's what it is. So, example, tastes as good as a real thing. The makers of a Diet Cola claim that the taste of the Diet Cola is indistinguishable from the full calorie version. Yeah, right. To investigate, some AP Stats kids prepared small samples of each type in identical cups, then had volunteers taste each cup in a random order and have them try it. You know what? I don't have time to do this one. I'm going to have to do this on the next video. I'm sorry.